So today we continue looking at what we call projectile motion. If I have enough time, I'm going to include free fall because it's almost one concept. It's just that free fall we're also talking about one dimension, which is the vertical axis. But when we talk about projectile motion, this is motion that is actually existing in more than one dimension. I had explained to you last week to say we have different kinds of motion. We have motion in a straight line, which we discussed last week. And I also mentioned to say we're going to look at motion in more than one dimension, of which in this case, we're going to focus on motion in two dimensions. So let's imagine you are throwing a stone. We used to do this a lot when we were kids, or not just a stone. Maybe you're firing a catapult, or maybe you're firing a gun, whatever you do. You throw it from the ground, but you don't throw it straight up. You throw it at an angle. You're going to notice that that particular object is going to travel, going up. It will reach a certain point, and it will start going down again until it hits the level ground, until it hits the ground. So this kind of motion, if you look at it, if I draw my x or y plane at the initial point here, let me call this point. Okay, so let's say this is my x-axis, and this is my y-axis, or rather, this is my x-axis, and this is my y-axis. You're going to notice that this kind of motion will not just flow in one dimension. You are throwing something forward, and that particular object is going to be going forward, whilst at the same time it will be going up. Then it will reach a certain point where it will be going forward, whilst at the same point it will be going down. So this kind of motion is what we call motion in two dimensions. And in particular, today's topic, we're going to call this projectile motion. So the object that you are going to throw, the actual object that will be throwing and that will be undergoing this motion is what we call a projectile. The object undergoing this type of motion is what we call a projectile. And this black path that I've drawn here, the path that this object is going to follow, is what we call a trajectory. So this path, this black path here is what we're calling a trajectory, and we can call a projectile maybe the actual substance that has been thrown. Let me represent it here with this red dot. So if you look at this diagram now, you're going to notice that from what I'm explaining, we're having both motion in the y-axis and motion in the x-axis. And these are the actual things that we're going to talk about. We're going to talk about motion in the vertical axis and the motion in the horizontal axis. And we're going to discuss the components of all these kinds of all these two types of motion. So if we talk about motion in the vertical axis, you're going to notice that in this axis, there is a force of acceleration. There's a pull of acceleration, and that pull of acceleration is always pointing down due to the Earth's atmosphere. And what do we call that a force of acceleration? We call it gravity. G, with a magnitude of 9.81 meters per second squared. So that guy gravity is always pointing down. It is a force of acceleration that is always pointing down. And you're going to notice that this guy is actually existing in the y-axis and in the y-axis only. It is pointing down. That means it doesn't affect the motion that is in the horizontal axis. It is only existing in the vertical axis. So when you throw an object going up, what are you going to notice? You're going to notice that since the force of gravity is pointing down, that object will be going against this force of acceleration. As a result, instead of this guy acting as acceleration, if an object is going up, it is going to act as the force of deceleration. It is going to be decelerating that object, hence reducing its velocity, the initial velocity that was given here. Let me just call this V0 as the initial velocity that this object is given as you are throwing it here. So in the y-axis, that initial velocity is going to be experiencing a force of deceleration, and it will be reducing its velocity until it reaches a point where the velocity of that object is zero. That is in the vertical axis. So when it reaches this point, which we call the maximum height, we do this. When it reaches this point that I can call the maximum height here in the vertical axis, or the maximum displacement in the vertical axis, when we reach the maximum height, the velocity in the y-axis is actually equal to 0 meters per second. The velocity of that particular object is equal to 0 meters per second because it has reached its maximum height, which means the initial velocity that you gave this object in the y-axis has actually been overdealt with. Hence, it has reached 0, and it is going to stop. It is going to just stop. I think by now you understand what we mean when we say just stop. It means it's just going to stop for an instant, and it will start gaining momentum again. It will start gaining velocity, going down until it hits the ground with a certain velocity. So this type of projectile that I've given you here, or that I've drawn for you here, is what we call the symmetrical projectile motion. This is symmetrical projectile motion because it is having a line of symmetry, and you can divide this diagram into, you can actually fold it into two and come up with two equal parts. So when it reaches that point here, the maximum height, we say the velocity of that particular object in the y-axis is equal to 0. Then it will start, or it will just stop for an instant. Then it will start gaining velocity again, going down in that direction. So this guy that we see, we call it the H max, or the maximum height. And since the velocity that we were given here, the initial velocity, was given at an angle theta here, we are from talking about vectors, and we explained to say when we have a vector existing in both the components, the x and the y components, what do you do to start to that particular vector? You have to resolve it to its components. It is existing in the x and the y axis. So what do we do? We resolve it into its x and the y components respective. And how do we do that? We already looked at how to resolve vectors to its respective components, or how to resolve a vector into its respective components. Because this particular vector that we've been given, since velocity is a vector, we know by now, is going to exist in the x-axis. So we're going to call that Vx, or V initial in the x. And it is also going to exist in the y-axis. So we're going to call that V initial in the y. And since the x-axis is the one which is adjacent with this theta that we have here, the x-axis is the one which is going to carry a cosine. We already discussed this last week. So we are going to say the component of velocity, or the component of initial velocity in the x-axis, will be equal to V initial cos theta. Whilst the vertical component of our initial velocity will be V initial sine theta, which means if you're dealing with the x-axis only, you're going to use this as your initial velocity. If you're dealing with the y-axis only, you're going to use this as your initial velocity. And since we've said gravity is only existing in the y-axis, one thing you're also going to notice is that it doesn't affect the motion in the x-axis. It is only existing in the vertical axis, which is the y-axis. Hence, it is not going to disturb anything in the x-axis. What does that imply? That means the same velocity that you have at this initial point here in the x-axis will be the same velocity that you are going to have at the final point there in the x-axis, which means final velocity, or initial velocity in the x, is equal to final velocity in the x, because there is actually no force of acceleration acting in the x-axis. The gravity is only existing in the y-axis, hence it doesn't affect any motion in the x-axis. So we're going to say V initial in the x. This will be the same as V final in the x. I hope we're together. Whilst the velocity that we have, the velocity, or the component of velocity that we're going to have in the y-axis, will be experiencing constant changes. Why? It's because we are having a constant force of acceleration acting on it. It will be pulling it down until it stops. Then it will start going along the force of acceleration, hence gaining momentum until that particular object hits the ground. So from the things that are in the horizontal axis, or in the vertical axis, let's start with the vertical axis. I hope you'll be able to remember this diagram because I'm trying to go a bit down. Let's say vertical motion. Let's look at vertical motion. So one of the things that we're going to look to find to the components of vertical motion is that we're going to have initial velocity in the y, v initial in the y, which will be equal to what? It will be equal to the initial velocity that we've been given, sine theta. Then we can also look at the displacement in the y, the maximum displacement in the y, d max in the y. is this guy that I've labeled as the maximum height. So which means the maximum displacement in the y is equal to h max. And you're also going to notice that in order for that object to travel from its initial point here, from the initial point here, up to that maximum point where the final velocity will be 0. I can just call this the initial point and I'll call that the final point, where the final velocity in the y will be 0. This guy is going to travel and is going to take time t, which we're going to call time of flight, up to the maximum height. So since this is a symmetrical diagram, I've told you to say the same characteristics that we are going to have on the left-hand side here are going to be the same things that we're going to have on the right-hand side here. So if we calculate time up to that maximum point there where final velocity in the y is 0, we can just multiply that time by 2 to get the total time from this initial point up to that final point. I hope that is clear. So let's look at how we're going to derive the equations now for calculating these components of motion in the vertical axis, or the components of motion in the vertical, in the y-axis rather. So when I was explaining to you the Soviet equations on Saturday, I explained to you to say we have those equations, which we call the Soviet equations, which are used when acceleration is constant, when there's constant acceleration. And it's the same case here, because acceleration is constant. It's equivalent to 9.81 times the meters per second squared, not times. I'm used to dealing with exponentials. So that value of acceleration is constant during this whole motion in the y-axis particular. So what are we going to notice? We're going to apply those same equations that we talked about last week, the equations that I used in or on motion in a straight line, which we call the Soviet equation. So one of the Soviet equations that we discussed was this one. It said final velocity is equal to initial velocity plus acceleration multiplied by time. This equation is used to calculate final velocity. Now, let's manipulate this equation in order for us to find the equation that we are going to use to calculate time of flight. And how are we going to do that? We're just going to replace whatever is in this equation with these things that we've talked about here, including the value of gravity that we have, of which when going up, you'll be going against gravity, so it will be negative gravity, whilst when you are going down, that's when it will be positive. So it will be positive when going down, whilst it will be negative when going up. So let's manipulate this equation that I've written on the right here to come up with the equation that we're going to use to calculate time of flight from the ground up to the maximum displacement in the y-axis. So the value of our initial velocity and final velocity are already known, because we said since this object is coming to a stop at its maximum height, the final velocity in the y will be equal to what? Will be equal to 0 meters per second. And the initial velocity is going to be equal to what? It's going to be a resolved version of the given velocity. So this is going to be equal to what? This is going to be equal to v sine theta, like that. The acceleration that we're talking about is the gravity that is here. And since this object is going up initially, this gravity is going to be negative. Then we have the time that we are looking for there. So first things first, let's plug in what we've talked about. Let's not put a lot of things. So I'll say my final velocity, which is 0, will be equal to my initial velocity, which is v sine theta, or I can just say u sine theta, because u is the one which is used to represent initial velocity. U sine theta plus, or let me not say plus, since I'm putting a negative, I can just put a minus g, this guy that is here, multiplied by t, like that. This is the equation that I'm going to end up with. And from here now, I can make my t, which is time, the subject to the formula. What am I going to do? I'm going to take this part of the equation, which is negative, and take it to the right-hand side of my equation. I'm going to end up with gt being equal to u sine theta. Then from here, I'm going to say divided by g on this side, even this side, divided by g. G and g will cancel out, hence my time of flight will be equal to what? Will be equal to u sine theta divided by gravity. And this is the equation that we're going to use to calculate time of flight. This is the equation that we're going to use to calculate the time of flight. And which time of flight is that? Is only the time from when this object is thrown on the ground to when this object reaches its maximum height here. Because at the maximum height, that's why we have our final velocity as 0. And since we found now the time of flight that is required to 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 travel from the ground to the maximum height, we can also find the time of flight, or we can calculate the time of flight for the whole motion up to when it hits the ground here at this point. How are we going to do that? We're just going to multiply this equation that we found here by 2. So I'm going to say this equation by 2. It will give us the total time of flight of the whole motion until the object hits the ground. So this guy will be multiplied by 2. And at the end, what are we going to have? We're going to have time of flight, total time of flight. Let me write this equation here. Total time of flight will be equal to T will be equal to, I'll multiply this by 2 u sine theta divided by g. So this is, ladies and gentlemen, the equation that is going to give us the total time of flight from the time you launch your projectile at this point up to the time it hits the level ground. The level ground, I repeat, the level ground, since we are just looking at the symmetrical diagram of a projectile motion. Okay, so this was the first thing. The second thing that we can calculate is the maximum height itself. H max. So how do we calculate the maximum height in or on a projectile? So we're going to use this equation from the Soviet equation. We said v squared is equal to u squared plus 2as, where s here is the displacement. And this is the guy that we are looking for, since we are looking for displacement in the y component. So we're looking for s in this case, and we're going to do the same to this equation. Let's manipulate it and try to find the equation that we're going to have at the end point. So remember, we said at the maximum height, final velocity is equal to 0. So we're going to do the same. We're going to plug 0 where there is maximum velocity v there. Then this will be equal to u squared. And we said u in the y-axis will be equal to what? Will be equal to u sine theta. I'm going to put this guy in squared in brackets and square it, since we have a square there. Then plus, or I can already put a minus, since the acceleration that I'm going to use here is still for the motion of this particular object going up. So this is still going to be negative g. The 2 here is a constant. So what am I going to have? I'm going to have minus g, or I can just say minus 2. Let me put the 2 in front, since it's in front here. 2gs. What are we looking for? We're looking for s. But since in this case it's maximum height, let's represent it with what? With h. We are looking for maximum height. From here, let's take this negative part to the left-hand side of the equation. So we're going to have 2gh being equal to u sine theta squared on the right-hand side. Okay, now the equation has even been simplified, because we're just going to divide this side by 2g, even this side by 2g, and we're going to find our equations for final equation for calculating maximum height as being equal to u sine theta, this is squared, over 2g. So when you're asked to calculate the maximum height that a projectile is going to travel after being thrown from a certain height, or it can be the level ground or whatever height that projectile is thrown from, the formula for calculating the maximum height that projectile will be able to travel is u sine theta in brackets squared divided by 2g. If you want, you can resolve this equation further, but it's actually not necessary, because you just start complicating your own life. If you want, you can say this will be equal to h being equal to u squared sine squared theta. You are just distributing the square outside, divided by 2g, of which this is the same as this guy who is on top here, of which if you put everything in brackets and square it, it is simpler than using this kind of an equation or this form of an equation. So I highly recommend this one, which is on top here, other than the one which is the distributed one, the one which you are having our square distributed. So ladies and gentlemen, those are some of the components that we're going to have in our vertical axis. When you're dealing with motion in the vertical axis, we can calculate time of flight, and we can also calculate the maximum height. This is the equation for calculating maximum height, whilst the previous one found is the one for calculating time of flight. So total time of flight will be equal to what? Will be equal to 2 u sine theta over g. These are the two equations that are particularly used in the vertical axis. Now let's go to the horizontal axis. Let's go to the horizontal motion. Okay, so one of the interesting facts of the horizontal motion is that it doesn't get affected with with the gravitational force that we've already talked about. Okay, so since this guy is not affected is not affected with the force of acceleration, which is gravitation in this case, we're going to find that the final velocity or the initial velocity that we have in the x will be the same as the final velocity that you're going to have in the x. Velocity doesn't change in the x-axis. And you're going to notice that as this object is moving from the initial point up to the time it hits the ground, it is going to cover some distance here. It is going to cover distance from this point all the way up to where this object is actually going to hit the ground. And we call this displacement in the x-axis. And this displacement in the x-axis is referred to as the range of your projectile. So this will be the range of your projectile. So this is the only thing that we are going to focus on when we talk about the horizontal motion, because we've already calculated time, how time is calculated, and time is the same in both the x and the y axis. So since we've already known how to calculate time on projectile motion, that means in the x axis there will be distance that will be covered with time. We already know how to calculate time. Now let's learn how to calculate the distance that is covered in the x axis, or the horizontal displacement, which is referred to as the range of your projectile. So we are going to use the same equations that we talked about, that we discussed in the other day on Saturday. So we're going to say distance will be equal to speed multiplied by time. We've already found the equation for calculating time. So what are we going to do? We're going to say distance, for which this distance is range, this is the x-axis, will be equal to the speed in the x-axis. So how did we say we have to resolve the speed in the x-axis, and it is going to turn into what? It's going to turn into u cos theta, and this is going to be multiplied by time. And the equation that we found for calculating time is the one that we're going to plug here. And since range is going to be covered, or it's going to be covered after the total time of flight is elapsed, we're going to use the final equation, which we multiplied by a 2. So that means we're going to multiply this guy with what? With this equation that I have here. This one, 2 u sine theta over g. This is the equation that I'm going to multiply this by. So I'm going to say this multiplied by 2 u sine theta over g, like this. And what am I going to end up with? I'm multiplying u and u here. That means I'm going to have u squared, which means this equation is going to translate into 2 u squared cos theta sine theta, like this, over g. This is the equation we use for calculating range. But if you look at your mathematics, if you've done trigonometry, I don't know if you're going to do it or if you've already done it, we have what we call trigonometric identities. And one of the trigonometric identities we have is that this expression, 2 sine theta cos theta, which is the same as this one which you have here, cos theta sine theta. It's the same, it's commutative since we're multiplying here. 2 sine theta cos theta will be the same as sine 2 theta. This is a trigonometric identity, and we are going to apply it in physics now. We are going to learn it in mathematics. I don't know if you've already done it, or if it is in your syllabus, you are still going to cover it. But 2 sine theta cos theta is equal to sine 2 theta. And if we look at our numerator here, we are having this part which is telling us about 2 cos theta sine theta. We have 2 here, we have cos theta here, and we have sine theta here. So we are going to replace these three guys with this single guy that we have here, which is sine 2 theta. So which means my final equation is going to be equal to what? My final equation for range will be r being equal to u squared, since u squared is going to remain. Then the remaining things will be replaced to sine 2 theta, u squared, sine 2 theta over gravity. And that, ladies and gentlemen, is the formula that we use to calculate our range. This is the formula that we use to calculate our range. And if I reach this point, I think I've discussed all the formulas that you are supposed to know under the symmetrical diagram of projectile motion. But it's not all the time that you're going to be given the symmetrical diagram of projectile motion, because sometimes they'll tell you to say a projectile started from a rooftop, or it started from a vertical surface like this. Then it went like that until it hits the ground. Sometimes they'll tell you to say it started from the ground itself, then it was thrown up until it hits the top of a building. Sometimes it can be like how? And this is the only two. Okay, sometimes it is going to start from the same top of a building, for example, then it will be thrown up, then it will travel a certain distance, then it will start falling down until it hits the ground. These are the types of projectile motion that you are going to be given. So how many are there in total? There is one, this one, there is two, this one, there is three, this one. Then there is the fourth one, which is the symmetrical diagram, the one that I drew for you there. So the same formulas apply when it comes to this one and this one mostly. But when you're looking at this one where your projectile is starting from a flat table, you give an example of a flat table, you push something from a flat table, then it rolls, then it falls like this using this diagram B, or diagram number 2. You're going to notice that the velocity that you're going to have, since the initial velocity is only in the x-axis, there will be zero velocity at the initial point in the x-axis at this point here. So we're going to have the velocity that this object is going to have will only be in the x-axis. There will be no velocity in the y-axis, since at the initial point it is just moving horizontally before it starts being acted upon by gravity and starts falling to the ground. So these are the kinds of projectile motion questions that you're going to be asked wherever you go in the world. And if you know these formulas, ladies and gentlemen, you can never fail to answer a question on projectile motion, because they always come like this. I've seen this one where they ask you on a basketball, you throw, then it goes into the basket, blah, blah, blah. You're going to use that one. You throw something from the top of a building, or if a volcano erupts, it's going to use this one. It is going to go up initially, then it starts falling down. If you push something from a table, a horizontal table or horizontal building, or you fire a bullet horizontally first, it's going to travel using this second one. Whilst if it's a symmetrical one, you throw something from a level ground, then it is also going to hit the level ground. It is going to use the symmetrical diagram that we talked about in the first place. So that is the theory or all the concepts that I wanted you to know under projectile motion.